Pharmacokinetics. Now, today we will start pharmacodynamics. You know that pharmacokinetics actually included absorption, distribution, metabolism, and excretion. And this pharmacokinetics means the way body reacts to the exogenous compound drug. And pharmacodynamics means how drug affects biological system, our body. So this you may call actually the drug action, which may be largely it is used for the therapeutic effect, but it may result in side effects or toxic effects too. The most common mechanism of drug action is drug receptor binding. Activation or antagonism, inhibition of certain receptors present on the cell surface, largely on the cell surface. They may be present within the cells as well. The other mechanism, which is also, of course, less common than the previous one, but is still a common mechanism, is activation or inhibition of certain enzymes. And the third one, which is an unconventional mechanism, is the mechanism by which individual drugs actually act. So drug receptor interaction and activation or inhibition of enzyme is the most common mechanism of drug action. Enzymes as well as receptors, they both are proteins. So in fact, this is drug-protein interaction in a way, in both ways. Now here you can see drug-receptor interaction. Receptors which may be present inside the cell, but here they are present on the surface of the cell. An extracellular signal which may be endogenous or exogenous, it binds with the receptors and a cascade of events start. This may result in simply a quick response, cellular response, that is some changes in the concentration or activation of various enzymes presented here in the cytoplasm, or a long-term effect which may take place because the complex which is formed here, it permeates nucleus and some changes are produced in the messenger RNA formation. So long-term changes are produced in terms of altered gene expression, while short-term changes are produced in terms of certain enzymes or in cytoplasmic reactions, enzymes which are present in the cytoplasm. And altogether, both of these will result in the formation of altered function, altered behavior, and all that. Clear? Here you can see the drug affecting enzyme activity. The examples which are shown here are of physostigmine and neostigmine. They both are the drugs which inhibit activity of acetylcholine esterase. Acetylcholine esterase is an enzyme which degrades acetylcholine. Acetylcholine, once it is released in the synapse, it binds with the receptors, cholinergic receptors we will say, and it produces an action. So a drug which inhibits this enzyme, acetylcholine esterase, acetylcholine which is released here will be degraded by acetylcholine esterase into choline and acetic acid. Choline is recycled. So a drug which inhibits the activity of acetylcholinesterase means the degradation will not take place, means the life of acetylcholine in the synapse will increase and cholinergic function will also increase. So these two drugs, physostigmine and neostigmine, they differ in their blood-brain barrier permeability. Neostigmine cannot permeate blood-brain barriers, while physostigmine can. So this is particularly used when there is impaired or low cholinergic function in the brain. Do you know any disease in which cholinergic function in the brain is reduced? It's dementia and Alzheimer's disease. Acetylcholine is known to have a role in memory function, and cholinergic neurons are degenerated in Alzheimer's disease. Their function is reduced in dementia. So physostigmine, of course, you cannot replace the cholinergic neurons in Alzheimer's disease by physostigmine, but the activity of those cholinergic neurons which are alive in there, which survive, their activity is enhanced. Neostigmine cannot permeate blood-brain barrier. It is used in those cholinergic reduced cholinergic activity of the periphery. In fact, for example, in myasthenia gravis, the cholinergic function for cholinergic receptors in the muscles, they are degenerated, and in that it is used. Because both of these drugs will increase the life of acetylcholine. So cholinergic functions are enhanced. The third mechanism, unconventional mechanism, like antacids, they don't bind with any receptors, they don't inhibit or activate any enzyme, but they just neutralize the pH of the stomach. They increase the pH of the stomach. Aluminum hydroxide, magnesium hydroxide, sodium bicarbonate, and calcium carbonate, these are the examples. Vinca alkaloids, these are used for the cancer chemotherapy, and they inhibit the cell division in the phase of mitosis. Those cells which are actively dividing in the tumor cell, so their division is inhibited. Chelating agent, EDTA, this is used in cases of lead poisoning. It is injected systemically, and then it binds with the lead, and there is excess of lead. It will interfere with oxidative phosphorylation and all other reactions too, and then that may be lethal sometimes. And in general, it reduces memory function. So they bind with the lead and reduce the free lead available for acting on various reactions. Vaccines, they act as antigen and they enhance the production of antibodies. You can see here the action of antacids. Sodium bicarbonate, it will ionize into sodium and bicarbonate ions. Sodium will be reabsorbed. Bicarbonate ions, they will combine with the hydrogen ions present in the stomach to form carbonic acid, and carbonic acid is a weak acid. Unlike HCl, carbonic acid is a weak acid, so therefore the acidity of the stomach is reduced. Similarly, calcium carbonate, magnesium hydroxide, and aluminum hydroxide, they reduce the pH of the stomach, and they have different side effects. You can see here. Vinca alkaloids, the chemotherapeutic agent, it inhibits the cell division and mitosis. These are the various phases of cell division. The formation of a spindle is inhibited. Vaccines, they enhance the formation of antibodies, ADTA, binds with lead. Let's come to the drug receptor binding, which is the most common mechanism of drug action. And most of these receptors with which drug produce their effects, they are present on the cell surface. So receptors, what are receptors?
Regulatory molecules, protein molecules.
Regulatory protein molecules largely present on the cell surface, sometimes inside the cell chamber. Target cell.
That is the receptors, specific receptors are present to which the drug or normal endogenous compound bind.
Which is targeted by endogenous or exogenous compound because the receptors are present in there. And drug receptor interaction. The drug receptor interaction is usually a reversible reaction, means drug will occupy the receptor site and immediately it will be released from that site. Okay? But sometimes the reaction is irreversible too. In that case, the receptors are permanently eliminated from the system. Agonists.
Endogenous compound
The cell reaction.
same for
Agonist.
Makes the action.
Agonists are endogenous.
Enhance the cell
It mimics the action of endogenous compound.
It's drugs which act in the same way as the endogenous compound. They produce a response similar to endogenous compounds. They bind with the receptor sites and produce a response similar to endogenous compound. They are called as agonists. Drugs which bind with the receptor sites, but what?
but lowers the activity.
But produce no response. Okay? But produce no response, they are called as antagonists. They bind with the receptor sites, but produce no response. So, actually, why an agonist produces a response and antagonist produces no response? So, the both of them, they bind to the receptor sites.
Structurally different. They are
Signal
structurally
transmission
different.
signal transmission system which involved in the agonists, whereas not in antagonists.
They are really different.
Agonists, they bind with the receptor sites, but they bind with the receptor sites and activate the receptor site so that it can bind with the transducer system. It can activate and reduce the transducer system. While antagonists, they occupy the receptor site but are unable to activate a transducer system. Okay? So they don't produce a response. But at high concentration of an antagonist, the basal response is reduced. Why?
Because they occupy most of the receptor sites, so that the normal, because they occupy most of the receptor sites and the normal endogenous compounds will not bind and normal function will be reduced.
So they occupy the sites which were previously occupied by the endogenous compound. So the endogenous response, the basal response is not produced. Now let's see characteristics of drug receptor binding. The binding is saturable, means as we go on increasing the concentration of agonist, the binding will increase and it will reach to a plateau. When further increase in the drug dose will produce no increase in the binding. And you know this is because of the
Receptors are occupied.
saturation of the receptor sites. Receptor sites are saturated, all of the receptor sites are occupied by the drug and are no more available. The binding is reversible and obeys mass law, means drug plus receptor is equal to drug receptor complex and then the reverse reaction. And the other thing that the ligand or the drug should bind to the receptor sites at very low concentration. Okay, very low concentration of the drug should be able to bind with the receptors, otherwise it is non-specific binding. And lastly, the binding should produce a pharmacological response. The binding should result in a pharmacological response. You will say that agonist produces a response, antagonist will not produce a response. So, what will be the pharmacological response here? The binding should result in a pharmacological response. Means a response which is produced by an agonist should be inhibited by an antagonist. Okay? A drug binds with the receptor sites, produces a pharmacological response. It is an agonist. A drug binds with the receptor sites at low concentration, but is not producing any pharmacological response. You will not say that it's non-specific response, but you have to test it whether it is inhibiting an agonist response or not. So if these criteria are not fulfilled, the data may indicate the existence of non-specific binding drug, because a drug may bind to those sites, which is to proteins, to a number of proteins at high concentration, and those proteins are not in fact receptor proteins. Okay? These are the binding sources which are responsible for drug receptor interaction. Mainly weak forces play a role, like control forces between two molecules, hydrophobic interaction between two hydrophobic molecules. The drug is a hydrophobic molecule and receptor site has got a hydrophobic site. Hydrogen bonding may occur. So ionic bond means ionic attraction, not really ionic bond, but ionic attraction, plus and minus charges may attract each other. And in this way, these weak forces may have a role, or not only one force, multiple forces may be involved in the binding. And from these sites, the drugs are released. Sometimes the binding may be overreached. Here you can see the description of various types of forces. Now let's define affinity. We know that a ligand, here we will say a drug or ligand, will bind with the receptor sites to form drug receptor complex. This is the rate of forward reaction, rate of backward reaction. And the dissociation constant is given by what? K minus 1 divided by K1. This is the dissociation constant. And K minus 1 divided by K1 is the dissociation constant. And the reciprocal of Kg is the association constant, Ka. So affinity, how you define affinity? force with which a drug binds with the receptors is called its affinity, and it's reciprocal, it's inversely proportional to dissociation. The force with which it will bind to the receptor sites will be just inverse of dissociation. Agonist and antagonist. A drug binds to the receptor site as an agonist or an antagonist. So both agonist and antagonist have got affinity. And agonist will bind to the receptor sites and will activate it, while antagonist will bind to the receptor sites and will not activate it. Now here you can see the examples of agonist and antagonists. Acetylcholine, and this is the cholinergic receptors, the binding sites. Acetylcholine will bind with the receptor sites because of the ionic force, okay, and the hydrogen bonding. The agonist of acetylcholine, carbacholine and pilocarpine, they can bind with the receptor sites with this, the ionic interaction, and hydrogen bonding, both of these, okay. The antagonist, it could bind with the receptor sites because of the either with the ionic attraction, okay, or with the hydrogen bonding, but the two at a time may not be occupied because of its three-dimensional structure. You can say the two sides are facing opposite each other. So activation of the receptor will not take place. The drug will bind with the receptor sites, but it will not activate the receptors. There are other terms too. Inverse agonist. A drug binds with the receptor sites and produces a response just inverse to the basal response. Okay? Opposite to the basal response. For example, if a drug, for example, you can say the adrenaline and noradrenaline, they increase blood pressure. So if a drug binds with these receptor sites and reduces blood pressure, you cannot always say that this is an antagonist, but this may be inverse agonist too. Partial agonist, a drug binds with the receptor sites but will not produce full response. Then it will be a partial agonist. Maximum response is not produced. So the drug receptor binding may be an agonist binding, response similar to the endogenous compound. Antagonist binding, no response at low doses. Inverse agonist, response opposite to the endogenous compound. And partial agonist means response is same as the endogenous compound but not maximum. Why a drug binds with the receptor sites to produce a response? Because if a drug binds with the receptor sites and produces a response, it is said to have intrinsic activity, means it can activate the receptor sites. So agonists have got intrinsic activity, antagonists don't have intrinsic activity, and inverse agonists have intrinsic activity but of the opposite type. And partial agonists, they have got intrinsic activity but do not fully activate. Their intrinsic activity is smaller than the intrinsic activity of the endogenous compound. So here you can just differentiate affinity and intrinsic activity. affinity, the ability to bind with the receptor sites, and intrinsic activity, ability to activate a receptor site. Agonists have both affinity and intrinsic activity and may be specific for a population of receptors. Agonists may be specific, means, for example, there are acetylcholine binds with all the receptors. Different types of cholinergic receptors are there. Acetylcholine will bind with all these receptors to produce a response. But a drug may bind to only one population of cholinergic receptors, not all types of cholinergic receptors. Okay? So you can say this is the specificity of the drug. In other words, it could be non-specific. Non-specific doesn't mean that it will bind to all the cholinergic receptors. Non-specific means a drug may bind with cholinergic receptors as well as with other receptors like adrenergic receptors. So it will be said to be a non-specific. Okay? A drug may be specific for a particular type of receptor, or it may not be specific to receptors. It will bind to more than one type of receptors. Acetylcholine agonist at muscarinic as well as nicotinic cholinergic receptors. And muscarine is selective for muscarinic receptors. Nicotine is specific for nicotinic receptors. A cholinergic synapse, I'm not just moving through it. Are you aware of all these things, or any step is not clear? Because I have to finish it quickly. That's why I'm not. Is it okay?
Yes.
So cell surface receptors may be associated with a transducer system, and means the receptor binding may activate a G protein, okay, or other enzyme systems, while it may open or close an ion channel. And accordingly, they will be called as G protein coupled receptors and inotropic type of receptors. Inotropic and metabotropic receptors, or you can say ion channel coupled receptors and G protein coupled receptors. Here is the example of a G protein coupled receptor. Acetylcholine, which is released from the vagus nerve, it binds with the M2 type of receptors, muscarinic receptors, to inhibit the formation of cyclic AMP, and this results in decrease in heart rate. So atropine is an antagonist at these sites. It will result in an increase in heart rate. Okay, and this is sometimes used for just maintaining heart rate during anesthesia when the heart rate declines too much. So it is used to just accelerate heart rate. Ipratropium is an agonist. This too is used during anesthesia for just maintaining heart rate. Ipratropium and atropine both. Antagonists, they lack intrinsic activity because the drug receptor binding is not produced in the activation of transducer system. But at high concentration, antagonist can reduce basal response too. Here are the examples of competitive and non-competitive antagonists. This is the transmitter site. Transmitter binds with it to open the channel. Drug binds with these sites to produce to open the channel, it will be agonist. Antagonist can bind with these sites but produce no effect on this. This is competitive antagonist. It binds to the same site where the endogenous compound binds. Non-competitive antagonist will bind to another site, and although the site is occupied by the agonist, the channel will not open. Okay? Inverse agonist, the chemicals which produce just opposite effect to the agonist. So they have affinity, and you can say they have got negative intrinsic activity. Okay? Now here you can see the example of an inverse agonist. This is GABA receptor, GABA binding site. A number of binding sites are here. The main is for GABA receptors. This is GABA A receptor. Main is for GABA itself. So when GABA occupies this site, the channel will open. Chloride ion channel will open. Butyl is an antagonist. It will bind with the receptor sites. Channel will not open. And similarly, mucimol is an agonist. It will bind with the receptor sites, and the channel will remain open for larger time. There are sites for other compounds too. Indirect agonists like phenobarbital and pentobarbital, they bind and they increase the frequency of the opening of the channel. Okay. Picrotoxin, this is an inverse agonist. So it has got negative intrinsic activity. Okay, and this will produce convulsion. Okay, too much excitation. Benzodiazepines binding site is also there, and when benzodiazepines they bind, again the activity of GABA for these receptor sites increases. Means we have got an effect on increasing the duration of opening of chloride ion channel. Benzodiazepines, they bind with these sites, but an endogenous compound similar to benzodiazepine is not present. So these benzodiazepines are said to be inverse agonist. Means there is some compound present in the biological system which acts as an agonist, and it reduces the opening of chloride ion channel. Benzodiazepines, they just happen to bind to these sites and they increase the time of opening of this channel. Okay? A partial agonist will activate receptors to produce less effect. But just see here the full agonist, partial agonist and antagonist for the opioid receptors. Opioid receptors and the drugs which bind with the opioid receptors. Naloxone will bind as an antagonist, will produce no biological response.